Okay, so it's 12 right now, and I will begin to play the video of Tiny Tapeout. And thank you all for your patience. And here we go.
Hello everyone, I'm Matt Vann, and this is my talk about Tiny Tapeout for COSCUP 2025. Today I'm going to be giving a quick demonstration of Tiny Tapeout. I'll be looking at some of the coolest projects, taking a look at our community, the stuff that we've got going on at the moment, some exciting news and updates and things we're planning to do in the future. So let's get started. Now I'm sure a lot of you have already heard about Tiny Tapeout, but if you haven't, it's being recognised as one of the most valuable projects we have for semiconductor workforce development, and is getting quite a lot of take-up in academia and people using it for training. So what is the secret sauce behind Tiny Tapeout's success? Well, a large part of it is how easy we've made it to get the files you need to do a tapeout. So we call that ASICs in the cloud, and we leverage GitHub Actions. You create a project from one of our templates, you make a few updates, and then when you commit to the repository, an action runs, and what that means is it spins up a virtual machine, installs the open source tools, and then builds the files you need, the GDS files. And one single Tiny Tapeout tile, the smallest we do is 160 by 100 microns, which is about enough for 1,000 gates, and that then is ready to submit onto a Tiny Tapeout shuttle. So that brings me on to the other important thing, is running regular and cheap shuttles so you can get on board for just a few €100. Right now our chips are multi-project chips, and they support enough room for around 500 single tile designs. So you can see here's a single tile design. But we also support larger designs and mixed signal designs as well. And if you want all the information, then you can check out this IEEE paper that I published last year. So taking a look at some of our recent chips, and I'll share the link to this presentation later, and you can click on these links, but we've done more than 10 chips, and they look like this with all these little projects inside and some of these large ones. We're working with people in more than 30 countries, more than 50 universities. More than 100 designs have been proven to work. We've taped out about 1,500 designs, and we've interacted with around 5,000 people. Another really important part of the success of Tiny Tapeout, in my opinion, is the strength of the community, the people involved, and people helping each other out to do this new thing online. And we've just celebrated the 3,000th member of the Discord community, which is where we have our online community. And we recently ran a survey. We've got 680 odd responses, so you can see that most of our audience is in Europe and the US. That is predominantly 20 to 40-year-olds. We're kind of evenly split between academia and industry, and we still have a very strong kind of hobby hacker maker segment here. And people are using the service, and the majority of people are planning to tape out more than one design over the next couple of years. So especially as this is a recorded talk, it's much less risky for me to do a demo, so I thought it'd be fun to just show end-to-end what's involved in making a Tiny Tapeout submission the easiest way possible. So what I'm going to do is show everything that is required to end up at this stage, where you get one of our dev kits with the ASIC and your design on the ASIC, and then checking that it actually works. So we'll start off with the design, and here's a simple one made by Alexandra. And this is the kind of design that somebody might make in one of our Tiny Tapeout workshops, which I'll mention later. Experimenting with some logic gates and some flip-flops. So you can add any of these standard cell components here, these logic gates, and then we can put it into simulation mode here. So right now this LED is off, and I can trace this back to this AND gate, So I need to turn on in 0 and in 1 to get this light to flash on. There we go, this one turns on, that one turns off. And if I enable the clock, we can see these flip-flops starting to work, and then I have these two blinking lights at two different reds. So you can build a circuit like that with our schematic editor called Walkway, but you can also use a hardware description language. And then you create your repository. So here's the GitHub repository. And the important file here is the info.yaml that lists the ID of that design. And I've copied that repository and run the GitHub action recently, so everything's up to date. So this is what it looks like after success. It takes 5 minutes. There's no installation. You don't have to download anything. You get your utilization and wire length stats, a list of all the standard cells in use. So we saw quite a few flip-flops there. Were 16 of them, and I can click through to here and see the open source PDK, Skywater PDK, and the layout of the standard cells there. And then all the DRC and pre-check to make sure it's ready for manufacture. The 2D layout, and then my favorite is the 3D layout. One thing I always think is fascinating to see is how thin semiconductor designs are compared to their area. I can turn off all the fill cells, so now I just get left with the logic cells. And I can turn off the wiring. And then down here I've got a list of all these cells, so I could take a look at the AND gate that I saw. There it is there. And I can isolate that, so I can see what is actually going to be fabricated on a chip to make that AND gate that I just tested. Then that is submitted onto a Tiny Tapeout chip, so it's going to be forming one of these designs here. They all get manufactured. We manufactured this in November 2023, and we got the chips back in April. We manufactured them on the dev board and sent them out to people in June 2024. And then this is how we actually connect to it. So I have here Tiny Tapeout 5. I'll hold that up to the camera. Connect to the board. It reads the ID, so it can fetch a list of all of the designs. Logic Gates Tapeout by Alex. Then I press select to enable that. You see the lights change there. And then I can come to this interact tab. And then we'll see what happens if I turn on this one and that one. You see that top segment changing. And then let's see if I can get those lights flashing by enabling the clock. Let's choose a 10 kHz clock. And hopefully you can see that flashing there. So that's the entire journey from doing a design, getting the GDS files, submitting it to Tiny Tapeout and receiving your board and testing it. And then we encourage people to report the results so that we can track which designs are being tested and shown to work. Now that's a very simple project, and I want to demonstrate that Tiny Tapeout is also capable of some pretty advanced stuff as well. So here's some of my favorites. It's pretty useful for retro stuff. Probably a lot of you heard that the Z80 has been discontinued, and we put a Z80. This is a project by Ronaldus, and on Tiny Tapeout 7, and that has been just tested and shown to work. You can do pretty interesting mixed signal stuff. I really like looking at mixed signal stuff with the 3D viewer and being able to expand the layers. I think this black and white mode looks pretty cool as well. Being able to see inside and explore these very interesting mixed signal designs. And this design has also been proved to work. Recently, Sylvain Minot, who's a collaborator on the project, built a software-defined radio by using 2 Tiny Tapeout chips. One was a ADC and the other was a mixer, and he was able to get that working. So check the video if you're interested to know more about that. Another very impressive project is this Cayenne 5 RISC-V Micro Linux ASIC. So it requires an external flash memory to get enough RAM, but then it can boot Micro Linux and you can interact with it via the serial port. A very nicely documented microcontroller called Lisa, and this is an example of a very, quite a big project. You can see this big project here. It has used DFF RAMs for extra memory, and yeah, very nicely documented with a ton of information about how the whole processor works. So it's a great example of documentation. One of my favorites is a open source version of the 555 timer, and we can see that that is working with the classic charge and discharge waveforms. So those are just some of my top picks, but there's many, many interesting designs. And as I mentioned, we always encourage people to test their designs. And once you do that, your design goes into the Silicon Proven list that you can sort by shuttle, and we can see how many different people have reported the design is working. One of the things that we try to do is to keep all the tools online and accessible through the cloud, because that makes it a lot easier to run workshops and for people to get involved without the headache of downloading and installing tools. And some of you may have seen SiliWiz, so this is our tool for drawing and simulating MOSFETs and getting an understanding of how masks work. So let's see if I can draw a quick MOSFET for you. That's basically the essentials of it. But for me to test it, I'm going to need to make some connections. I should have a working simulation, so I can see that once I get past the threshold, the MOSFET starts turning on, and this orange line is plotting the current flowing between the source and the drain, and that allows me to very easily now explore the difference of making thinner or wider gates. And if you want to learn more about SiliWiz, then you can check out the lessons up here, and we've got lessons that will take you all the way through to drawing a CMOS inverter. But we're not satisfied there. We want to keep on innovating and making new tools. So one of them recently, which is contributed by Alexander Mortvintsev, is a very interesting tool that lets you visualize the circuit as it's running. And he just added this great 3D viewer mode, so we can now look into the circuit from different angles. And this is quite an interesting visualization, because up here on the left hand side you can also see this little dot, and that's doing the simulation of a cathode ray beam, so it's drawing the output. So as we speed this up, you can see it's drawing a pattern. So when you put this design into a computer screen, it's going to show this pattern. And it's really cool to see at the different speed levels. Up here we've got the clock divider, we've got the generation of the horizontal and the vertical sync pulses, and once we get to a certain speed, you can see the circuitry that is generating the pattern come to life. So a really fantastic tool from Alex there that allows you to explore what's actually happening when your design is running on silicon. And we've recently just updated our chip viewer So we are collaborating with Texplanes, who do security, reverse engineering and imaging. And on our new viewer now, this is Tiny Tapeout 7, you can zoom right down and get some really great images of the latest decapped chips. Here's these mixed signal designs. And you can also look at the different layers, so now we can take a look at the GDS. So there's that A to D I showed earlier. And then if one of these is interesting for you, you can turn on the project links, click through, and then load up the information about that specific project, look at it in the 3D viewer, get the source, and read the documentation. We have some really exciting projects on the way, including one that is putting Tiny Tapeout 6 into low Earth orbit. And this is a collaboration with Budapest University in Hungary. They have the infrastructure for a pocket cube format satellite, which is even smaller than a CubeSat. And there's room for, I think it's 1, 2, 3, 4, 5 small designs that all get soldered onto this pop-out flap. And our design here is this one, SpaceX, and it has Tiny Tapeout 6 chip on there. And the community came together and contributed about 20 different experiments that are going to be run in order once the satellite is in orbit. So we'll be able to test these designs and get the results of those tests while their satellite is going around. And they're expected to be in orbit for a couple of years. And if this project is successful, then we're probably going to do this for all our future chips. So not only are you able to submit a design that gets manufactured onto an ASIC, but also potentially you'll be able to test it in low Earth orbit, and all for this very low cost. We recently announced the crowdsourced RISC-V competition. We're providing a silicon-proven RISC-V core that's contributed by another community member called Mike Bell. And the competition is also a collaboration. We're building an open source microcontroller, and we're asking people to submit their peripherals. So it's free to enter, and you can get all the information there, and it closes on the 5th of September with a tape out on the 15th of September. So we've already seen 5 peripherals submitted already, and a lot of traction on social media. A lot of people are interested in taking part in this competition. So if you've always wanted to get involved but never really known exactly what to do, this competition is a really nice way of getting involved, building a collaborative project with the community, and then contributing to a chip that's going to get taped out imminently. Also coming soon is an FPGA board. So our dev kits have the yellow board on top with the ASIC on there, and we're doing a version with an FPGA. That's being designed by Patrick Deegan, who works with us doing a lot of our PCB work. And you're going to be able to commit your design into GitHub, as well as getting the GDS files. You'll get an FPGA bitstream. You'll be able to flesh that down onto that chip and test it on the dev kit. Order the ASIC, and when the ASIC comes, swap the FPGA for the ASIC. So talking of getting chips made, I think it's really important to have a regular and reliable shuttle service. If we want to see the world of open source silicon move on, people need to believe that they can make an order, that they're going to get a chip back in a reasonable amount of time, and that is a regular service. So for these more complicated IPs that take multiple tapeouts to get something good, that people are willing to put the effort in because they know that they can get their chips fabricated. So what is the current status? Well, we recently announced, I guess it was 6 months ago actually, collaboration with SwissChips and IHP. So we have ported Tiny Tapeout infrastructure to IHP, and that's thanks to CSEN, EPFL and ETH Zurich collaborating in this group called SwissChips. And we're running 4 shuttles. We've just got our first public shuttle open. It closes in roughly 30 days, I guess, by the time you're watching this. Check out the tinytapeout.com webpage for the current status. We've reserved half of the space for Swiss students, but the rest of it is available for you. And I was recently at the launch event, and we ran a successful Tiny Tapeout workshop there with 60 young people who took part and made tapeouts onto that chip. And it was great to see us being mentioned early on in the presentation. Our first IHP chips, we were able to tape out a fairly simple design and get that working, so that was a great pipe cleaner for us. And we've got another 2 chips on the way, and mixed signal analog support is coming soon. Now, probably a lot of you have heard that eFabless very sadly went out of business, and they were a very crucial part of the open source silicon ecosystem. And if we hadn't already been working with IHP, we would have lost our ability to get chips manufactured. So it's great news to share that 2 of the people who were involved with eFabless, Jeff and Mohammed, have started a new MPW service called ChipFoundry, and we are continuing to collaborate with them. And we are now running a shuttle which is taping out on the 15th of September, so plenty of time to get on board, and there's plenty of room left as well. And it's really good to have access to Sky 130 again. So that's Sky 130 and IHP 130, both very good processes to be doing open source semiconductors with. So I also want to share some exciting news regarding global foundries. So Waferspace is a new MPW being set up by Tim Ansell, who's very well known in the space and was involved with the original Google open sourcing of Sky 130. And he is committing Waferspace to support for adapting Tiny Tapeout to target GF180. We've also received good support from IEEE, the Electron Devices Society, and the other semiconductor-based societies. So far, we've got plenty of plans, and we're waiting to make some big announcements soon. And also very happy to say that we're getting support from Synopsys, who are also helping us with using Tiny Tapeout for GF180, and they plan to use that for the next generation of students in chip design. And I'm also very happy to announce that Tilitus has sponsored the development of GF180, so that work has now been started. We're going to be running a series of 4 chips building up to the full Tiny Tapeout infrastructure. So by 2026, you should be able to access 3 different fabs through Tiny Tapeout. So thanks very much for Tilitus, and we look forward to working with global foundries. So one of the things we're well known for is running big workshops with hundreds of students all doing a tapeout in just 4 hours. They start by drawing and simulating transistors using SiliWiz. They make a simple digital design with Walkway, they create the ASIC files with GitHub, and then they submit their design to be manufactured onto our chips. Here's a recent shot from a workshop I ran in Denmark, and this is some of the feedback that we get. People overwhelmingly have a great time and are amazed that they can get involved in semiconductors so easily. We aim to show them the tools, get them started, and then leave them a couple of weeks to be able to work on their designs. So up till the point of the tape out, they can continue to develop and iterate on their designs. And this is another shot from the Danish chip workshop that we ran that was very kindly sponsored by the Danish Chip Competence Centre, Edu4Chip, Synopsys, and Silosil. So many people who take the workshop are inspired to find out more about semiconductors, so it works as a really great way of recruiting people who are going to become part of the semiconductor workforce, and overwhelmingly people have a great time in the workshop. So it's a really good way of getting a lot of people to try out and experience the exciting world of semiconductors in a very easy and fun way. So that's about it for my presentation. I've just got a couple more things to share with you. The first is to invite you to ORConf, which is happening in September 12th to 14th in my home city of Valencia. There's going to be a lot of great talks there about open source silicon, It's organised by the Fossey Foundation. I'm helping to organise it. So don't delay, get your ticket and submit a proposal for a talk, and we'd love to have you there. I also want to promote the fact that I run a couple of courses. I've got the digital course and the analog course. These are the only practical courses that guarantee a tape out. So come and get involved, take one of my courses, support me and my work in the field of open source silicon. And connect with me. If you want to get these slides, you can go to the bit.ly link, bit.ly tt-coscup25, or scan the QR code. Sign up to my newsletter. Sign up to my YouTube channel, check out some of the great interviews and fab tours that I've been on. Connect with me on social media, and if you're in academia, I really appreciate citations on my IEEE paper. So thanks again, thanks Ruinland for inviting me. I'm really sorry I can't be there in person. I would love to come and visit you all and present my next talk in person, so let's try and make that happen for 2026. Otherwise, have a great rest of the event, and I hope to see you in Valencia for ORConf.